Let's tie in our discussion about market basket analysis, association rule mining, with our study of conditional probability, prior, posterior, those sorts of words. So we've talked about that the rules that we're after discovering are rules of the form: if a shopper has items x1, x2 through xn, a whole bunch of x's in their cart, then they may also have item y. So the words that we've used to describe these rules are the support and coverage of the rule. The support is the fraction of carts to which the rule applies. The coverage is the fraction of carts that have all items on the left-hand side, all of the x's. And we've talked about the confidence of the rule. So of all of those carts with all the x's, what fraction also have y? What's the probability that the rule is going to be correct once we stumble upon a cart that has all the items on the left-hand side? Now, it's worth talking more about the lift because it's really the lift that ties into our discussion about conditional probability, priors and posteriors. So let's go way back and revisit the multiplication rule for two events A and B, maybe having apples in a cart, having bananas in a cart. We know that the probability that two events occur simultaneously, A and B, can be written in one of two ways, both of which use a conditional probability. So the probability of A and B is the probability that A occurs, given that we know that B has occurred, times the probability that B has occurred, or just swapping the identities of A and B, same sort of rule. Now, if we were dealing with independent events, if the occurrence of event A is not at all influenced by whether or not B has or has not occurred, then this rule simplified because the conditional probability of A given B is just the unconditional probability of A itself. Knowing if B happened or not doesn't really matter. Now, if events A and B are independent, this formula simplifies. The probability that both events occur is just the product of the respective probabilities. And we've used this quite a bit. What's the probability of going 5 days in a row at UT without getting a parking ticket? If we assume the event of getting a ticket is independent from day to day, we multiply together the probability of not getting a ticket 5 times. What's the probability of getting a coin coming up heads on its first flip and its second flip? Well, we multiply together those 50%. So what if we took the viewpoint that shoppers were just picking items at random? They're going down the aisles, items are falling into their cart kind of at random with respect to the frequencies that shoppers purchase those sorts of items. Well, if it was the case that shoppers were purchasing items at random, then if we asked, well, what fraction of carts should have both items A and B, then it should work out to be the product of the two individual fractions, the fraction of carts that have A times the fraction of carts that have B. Now we can estimate these three quantities from the transactional data itself. We can estimate P of A and B by just looking at the fraction of carts that had both. We can estimate P of A by looking at the fraction of carts that have item A, and we can estimate PB by looking at the fraction of carts that have item B. So we can compare what we find on the left-hand side of that equation, the probability of A and B, with the product of the probability of A times the probability of B. If shoppers are basically purchasing items at random, we would expect those two numbers to match up. Now, when they don't, that's intriguing. That implies that either shoppers are purchasing the items together more frequently than what chance alone would lead us to suspect. And so this lift is going to be this number that describes how much more likely or less likely the shoppers are to purchase those two items together. So what do? Well, we take the probability that A and B occur together in the transactional data, the fraction of carts that have both, and divide it by the product of those two individual probabilities. That's what we're going to find to be the lift of the association rule. And if that lift is right at about 1, that means that the items are appearing in the cart about as often as what we would expect if shoppers were just picking items at random. If the lift is bigger than 1, well then they're appearing in the cart together more frequently than what chance would lead us to suspect. If the lift is less than 1, well the items are appearing less frequently than what chance alone would lead us to suspect here. So what types of items might have a lift bigger than 1? Well, spaghetti sauce and dry pasta. Those two items probably appear together in carts much more often together because there's an association between them than if shoppers were just picking those two items independently of one another at random. What items might have a lift that's less than 1? Well, think about Bounce dryer sheets and Bounty dryer sheets or Snuggles dryer sheets. It's unlikely that people are going to buy both brands of a particular product, so if we find Bounce dryer sheets in the cart, we're probably much less likely to see Snuggles dryer sheets than shoppers purely picking these items at random here. So the numerical value of the lift is something that we can use to quantify the strength of the association. And it's tied in really nicely to Bayes' formula for going from the prior probability of some event occurring to the posterior probability of some event occurring given some additional information. So one thing that we know is that Bayes' theorem lets us update a prior probability to a posterior probability once we're given new information. If I want to know, hey, I know item B is in this cart, what's the probability that A is also going to be in that cart? Bayes' theorem says, well, there's a mathematical procedure to do this updating. You can start with the prior probability that A is in the cart, P of A, and then multiply it by the ratio of two probabilities. And so that's going to be the role of the lift in this case. We're going to take the prior probability, just the overall fraction of carts that have that item, multiply it by the lift, and out will come the posterior probability. And so that's a great way of thinking about what the numerical value of what lift is telling us. So a few ways to interpret it. One way is that the prior probability of finding that item in the cart increases by a factor of lift to give you the posterior probability or the confidence. So your lift times more likely to find item A once you know that item B is in the cart. Or you can say that items A and B are appearing lift times more likely than we would expect if shoppers were purely picking items at random. So from chance alone here. And one important thing to note is that lift doesn't depend on the ordering of the items. If I think of the rule if A then B versus if B then A, those are both going to have the same lift. Mathematically, we can see that that works out. So kind of tying this all together, this terminology with market basket analysis, with Bayes' theorem, conditional probabilities, what we can do is we can take Bayes' theorem. Well, what's the probability that A is in the cart given that B is in the cart? Well, we can write that in terms of the support of item A, the prior probability that the item A is in the cart, and the lift of that rule. So what we find is that market basket analysis, the terms, are really just a restatement of Bayes' theorem. The confidence of our rule, if A then B or vice versa, can be given to us by multiplying together the lift and the support. So if I want to know something about what's the probability that A is going to be in a cart, I can take that prior probability, the support of A, multiply it by the lift of some rule that I have in mind, and out will come the posterior probability or the confidence. If the cart has B, then now here's the probability that we find A in it. So there's a nice connection with our discussion about conditional probabilities, market basket analysis. Market basket analysis fundamentally is really just looking at how transactions are structured using Bayes' rule. So kind of tying that back into the way we originally wrote our rules, if a shopper has a particular combination of items, x1, x2, all the way through xn, now what's the probability that we would find item y in that cart? So what's the conditional probability of y given x1 through xn? Using Bayes' theorem, grouping terms, and just replacing those terms with what we use in market basket analysis, we find that the posterior probability of finding y, the confidence of that rule, is just the lift of that rule times the support of y, the prior probability of finding y. And so there's that nice relationship between all of these terms we've been using in conditional probability and market basket analysis. So, concrete example, real world example. Let's imagine that we have some transactional data set and we're interested in studying the association between floss and toothpaste in shopping carts. These are items that we would think tend to get purchased together. We want to describe how strong that association is. So let's imagine that we have a total of 1,000 carts in our transactional data. It turns out that toothpaste is found in 50, floss is found in 20, and both items are found in 15 of those carts. So what are the implications? Well, let's think in terms of probabilities first. We could talk about the prior probability of finding floss in the cart. That would just be the fraction of carts that have floss, 20 out of 1,000, or 0.02, 2%. The prior probability of finding toothpaste would be 50 out of 1,000, or 5%. And so I want to talk about how those probabilities change once I know that the other item is actually in the cart. So the other probabilities that are relevant are the probability of finding both in the cart, that 15 out of 1,000, which is 1.5%. So what I'd like to know is, okay, well, what's the lift of the rule if toothpaste, then floss, or if floss, then toothpaste? Same lift, it doesn't depend on the ordering. And I can think about, well, how many times more likely am I finding both items in carts than shoppers picking items purely at random? So taking that ratio, the probability of finding both items in the cart, 15 out of 1,000, and dividing it by the supports of both items, the prior probabilities of each item, I would find that the lift is 15. So once I know that floss is in the cart, I'm 15 times more likely of finding toothpaste than if I didn't know anything about the cart composition, and vice versa. So what's another way of setting this up? Well, we could talk about specifically the rule, if a cart has floss, then they might have toothpaste. So what can we say is that the prior probability of finding toothpaste in a cart is 5%. Remember, fundamentally, the rule is always about the item to the right-hand side of the rule. So the prior probability of finding toothpaste is 5%. How does that change when we know that floss is in the cart? Well, the prior probability starts out at 5%. The lift is 15%. So the posterior probability, the confidence of that rule, is going to be 15 times the prior probability. 15 times 5% is 75%. That's by how much that probability of finding toothpaste in the cart has increased once we know that floss is inside that cart. All right, so the lift, even though we tend to talk about that number a lot when we do a market basket analysis, rules that have a large lift tend to be interesting to us because that means the probability of finding an item has vastly changed once we know something about that cart composition. The value of the lift does have a weakness in that there's a hard cap to what the lift of a particular rule might be based on the prior probability of finding the item on the right-hand side. So, for example, let's imagine that there's an item that most shoppers actually have in their carts. The prior probability of finding item A is 50%. Well, because the lift is the factor by which the prior probability increases to give you the posterior probability, or that confidence, well, since probabilities have to be 1 or smaller, we can see that we can at most only double that number. So any rule that we come up with A on the right-hand side of that rule, at best is going to have a lift of 2. Anything more than 2 would get a probability bigger than 100%. So whereas normally we gravitate towards these rules with a large lift, because that's telling us that the probability of finding the item is drastically changing with the cart composition, sometimes a small lift is actually pretty interesting. So depending on what the support of the item on the right-hand side of the rule is, that prior probability, sometimes a lift of 2 is quite intriguing. You know, if half the carts started out with item A, and now it's 100% of carts have item A with a lift of 2, Well, that's pretty darn interesting and potentially useful for us. One additional thing we need to be on the lookout for when doing a market basket analysis is whether or not the rules are statistically significant. So what do I mean by that? Well, with a large transactional database, with a lot of different items, there's a lot of different rules that we can examine, a lot of different rules that can be generated. And it might just happen that if we just throw a bunch of shoppers into that store, all picking items at random, there's going to be certain combinations of items that, just by random chance, happen to appear in carts a lot more frequently than if you had just multiplied together those prior probabilities. So we need to cross some sort of certain threshold, some certain number of cards that have both items to convince us that, hey, this isn't just due to kind of fortuitous circumstances and random chance. This is a rule that is statistically significant, very unlikely to have been produced by chance alone. And so we can gauge the statistical significance of a lift or a rule by asking the question, well, what is the probability that shoppers picking items completely at random would have produced a rule with a lift of at least as large as the one as we observed? This is what's known as the p-value of the lift, and we can actually figure out what that p-value is using what we've learned about counting. So let's imagine we wanted to figure out the p-value of this certain rule if A then B, or are shoppers purchasing items A and B together more frequently than what chance would suggest. Let's imagine that we have 15 total carts, 6 have A and 5 have B. What if I wanted to know the probability that exactly 2 of those 15 carts have both of those items in common? I want to know, is that a rare occurrence? Does this happen all the time? If I see 2 carts in my data set have both those items, is that something to take note of? Or is that just chance kind of working its way into the data? So how can I figure out the probability that exactly 2 of those 15 carts will have both items A and B? Well, for this illustration, let's just go ahead and arrange the carts as follows. Let's just have the first 6 carts in our sequence all have item A. And then what we'll do is we'll just randomly pick, okay, what are going to be those 5 carts that contain item B here. And so I've drawn one configuration where our event of interest has occurred, where we have exactly 2 carts that have both items A and B in it. So how can we figure out the probability of this occurring? Well, by that fundamental theorem of counting, we can split this up into 2 easier to answer questions. If I want to know, well, how many potential sequences have both A and B in it exactly 2 times? Well, I can actually say that really 2 things need to happen. So of the 6 carts that have item A in it, exactly 2 of those carts have to have item B. And of the remaining carts, basically the 15 minus 6 carts that don't have item A, we need to have 3 of those carts have item B. And we know how to count that. So of the 6 carts that have item A, there's going to be 6 choose 2 ways of placing item B in those carts. So that's one way to start it out. We have to have, of those 6 carts with A, exactly 2 containing B. There's 6 choose 2 ways of having that happen. And of the remaining carts, the remaining N minus NA, or the remaining 9 carts in this case, we need to select 3 of those to have item B. So there's 9 choose 3 ways of that occurring. So the product of those 2 will give us the total number of configurations where we have exactly 2 carts having both items A and B in it. We just need to divide that by some denominator. So since we're imagining that the shoppers are picking items at random, so which carts have item B are completely random, we just need to divide by the total number of configurations of how we can place 5 item Bs among those 15 carts. So 15 choose 6. So the p-value in this case, if we wanted to know, okay, is this noteworthy having 2 items or 2 carts with both items A and B in it? The p-value is the probability of getting at least 2 carts with both those items in it. The probability of getting a lift at least as big as what was observed. We'd have to take the probability of finding exactly 2 plus the probability of exactly 3, exactly 4, etc. So there'd be a lot of addition, a lot of choose. Luckily, we don't have to do this manually because there is a nice way to do this within the A rules package. Once we've developed those rules, we can say, okay, well, tell me, are these rules statistically significant? The command is.significant, if we pass it a set of rules in our transactions, it'll report back true or false. That'll let us know, okay, this is a rule that could readily be explained by shoppers picking items at random, or if it turns out to be true, this looks like it's a bona fide rule. This is not readily producible by just random chance alone. This could be something that you could actually act on. So how do we actually find all of these rules that are interesting to us? We've discussed that there's a phenomenal amount of combinations of items that in theory we would need to consider to see, all right, are shoppers purchasing these items more often than shoppers just picking items at random? So there's got to be some way to speed this up to eliminate a lot of combinations from consideration so we can find all of the combinations that would be interesting to us. So how does this work? Well, the a priori algorithm, in my opinion, is probably one of the top 10 machine learning artificial intelligence algorithms out there. Really revolutionized the field of association rule mining, market basket analysis, and so I want to explore how that works. So once again, we're going to try to discover rules of the following form. If a cart has a particular set of items, we'll call it the x's, x1, x2 through xn, then it may also have item y in it. So when we talk about the form of the rule, we talk about the antecedents and the consequent of the rule. The antecedents of the rule are just the set of x's. That's what's in the if statement of the rule. If a cart has this combination of items, these x's, then it may also have item y. Item y will be referred to as the consequent of the rule. Now, the length of the rule, we've discussed previously, it's the total number of items referenced in the rule. It's the number of x's plus 1, the one item being that y on the right-hand side. So we'll agree to restrict ourselves to finding rules where there's only one item in the consequent. And so how does this actually occur? So here's how the a priori algorithm works. And it relies on the user actually specifying what kind of rules they find interesting, that minimum support threshold, that minimum prevalence of what fraction of carts those rules have to apply to. Too rare, we don't care. So here's the key observation. If we think of some item set, say the combination of items A, B, C, and D, if an item set has a support that's below our support threshold of interest, then all rules involving that item set will also have a support below that threshold as well. So if we stumble upon a relatively rare item set, that's going to allow us to eliminate many rules and many other combinations from consideration. So, for example, let's imagine that we were only interested in finding rules that applied to at least 1% of transactions out there, a minimum support of 0.01. Well, if we find that items A and B appear together in only 0.8% of those carts below our support threshold, we can immediately eliminate all item sets that contain both A and B and all rules that reference A and B together. So we could eliminate if A then B from consideration. We could eliminate the rule if A and B then C from consideration. Or A and B and D and E implies G consideration as well. So if we run into a rare item set that allows us to essentially eliminate a vast amount of the search space as we're going through and trying to consider all of the possible item combinations there are. So there's a nice tree diagram that kind of builds up all of the possible combinations of items we would need to do in a market basket analysis. This is a pretty simple one containing only 5 items, A, B, C, and D. The top row has just carts with a single item in it. Here are carts with combinations of size 2, size 3, size 4, all 5 items. And here's how that eliminating the search space proceeds. So let's imagine that we find that item set AB is below our support threshold. We're only interested in rules that apply to 1% of carts, but item A and B appear in carts together only 0.8% of the time. So we automatically know that no rule involving item set AB is going to be interesting to us, and therefore any other item set that has both of those, all the item sets of size 3 that have both A and B, all item sets of size 4 that have A and B, and the one that had all 5 items, we can immediately just chop that off of the search space. And so in most transactional data sets, that's going to happen actually really quite quickly. We're going to stumble upon item sets fairly early on in the algorithm, item sets of size 2 or 3, that don't meet the support threshold, and that's going to allow us to immediately eliminate any higher order combinations that contain those items as well. So that's how you're able to quickly go through and generate all those rules you find interesting when you run the a priori algorithm, even though in theory there might be billions, trillions, even maybe more atoms in the observable universe, number of rules you could potentially generate. You're going to be able to quickly eliminate most of those because those are going to not be applicable enough to the carts based on your minimum support threshold. So one last, I think, really cool application for market basket analysis or association rule mining has nothing to do with studying shoppers' behaviors. Instead, it has to do with finding combinations of characteristics that tend to have a value that you find really interesting. Now, what do I mean by that? Let's look at a real-world data set. Let's imagine that we're interested in constructing a wine that's going to be very well received by everyone out there. In general, just gets a very high rating. Now, a wine can be characterized by some of its chemical properties, the amount of fixed acidity, volatile acidity, residual sugar, chlorides, alcohol, pH, etc. What if we wanted to discover particular combinations of these characteristics that are associated with a wine being considered high quality or maybe a wine being considered low quality? What combinations of traits tend to be associated with being high quality? Well, we can kind of treat our data set as a transactional data set if we just tweak our frame of reference. If we say, well, each wine is like a transaction, and its relative alcohol level, high versus low, let's say, is like having an item in the cart or not in the cart, having lots of alcohol, not having lots of alcohol in the cart, and considering these characteristics as items in the cart, we can just run that a priori algorithm, do a market basket analysis to see what combinations of characteristics, what items in the cart are associated with having the item quality equals high. Now, because these are all numerical predictors, we'll have to come up with categories to represent a range of values of these numbers. So like for fixed acidity, we might have to split this up into 5 different categories, like 3.9 to 5, 5 to 6, 6 to 7.5, etc. But then we can treat each one of those categories as an item in the transactional database and see what combinations of items are associated with being particularly high quality. So in the A-rules package, there's a fantastic command called discretize_df in all caps that'll take a data frame and it'll automatically come up with categories for all of the numerical predictors. So here, with this argument, I'm basically taking each numerical variable and coming up with 5 different categories with roughly the same number of wines inside each one of them. That's this method equals frequency. And I'm going to name those categories very low, low, average, high, and very high. So if I take a summary, here's the distribution of categories across all those chemical characteristics. And so if I wanted to study and find some sort of magic combination of characteristics that has a high probability of resulting in a wine of high quality, I can do the market basket analysis. Each wine is a shopping cart. Having citric acid is very low, residual sugar very high, are like having items in the cart. Let's find the associations. So we can convert the data frame into a transactional object that A-rules know how to work with, and then run the a priori algorithm. Let's say we're only interested in finding rules that have an 80% confidence. So basically, pockets of characteristics that have an 80% chance of having a high-quality wine that are relatively common in the data, so a support of 8%. These rules would apply to at least 8% of the wines in the data itself. And we'll make it not be too complicated. So if A, B, C, and D, then high quality. So 5 items referenced in the rule, a length of 5. Now, when we run this, we can take away the redundant rules, the rules that are not statistically significant, and in this case, we're left with 4 rules overall. So if we go and look at them, well, let's do some sort of interpretation. We're interested in identifying what it takes to make a wine high quality. Well, the first rule here says density equals very low, alcohol equals very high. This results in a pretty high confidence of having a wine that's high quality. Let's interpret this rule. Well, one thing that we know is that overall, a certain percentage of wines in the data are going to be high quality. If we get the item frequency of the item, quality equal high, we find that about 39% of wines are high quality. So the prior probability of finding a wine that's high quality is 39%. But what this rule is telling us is that if we know the density is very low and the alcohol is very high, that probability increases by a factor of the lift, 2.3, up to a posterior probability of 90.1%, the confidence. So the prior probability of having a high quality wine, about 39%. Among this particular type of characteristics, this combination, that probability skyrockets up to about 90%. And so we can scan down the list of rules and kind of figure out, well, what matters when it comes to having a wine be high quality. I would say one of the most common questions we run into in business analytics are, what are the main drivers of people churning, making a purchase, donating back to their alma mater? They want to know, what are the main drivers behind this process? Well, performing a market basket analysis and finding what combinations of characteristics of individuals are associated with a particularly high value of that characteristic is a great way to approach that problem here.